Colleagues, please take a seat. We are ready to start. We are ready to start the Jean-Dominique Cassini Medal Lecture. My name is Alberto Montanari. I have the privilege as EGU President to introduce the Union Medal Lectures, which is an honor because we celebrate with these lectures the achievements, lifetime achievements of our best scientists. I'm here today, as I said, to introduce the recipient of the Jean-Dominique Cassini EGU Medal 2019 and honorary membership, Margaret Kivelson. As you know, she received the medal yesterday during the EGU medal ceremony, so today I am introducing the medal lecture. From the citation, we know that Margaret Kivelson is receiving the Cassini Medal for her pioneering spacecraft-based investigation of magnetospheric plasmas to determine the natures of the interiors of planets and their moons. Kivelson led the team that discovered an ocean inside Jupiter's moon Europe, and a magnetic field generated by the solar system's largest moon, Ganymede, demonstrating that these moons have active interiors and potentially habitable environments. Her use of magnetometry to infer the presence of oceans has led to the recognition that habitable environments occur beyond the realm of the traditional habitable zone defined by the stability of liquid water on planetary surfaces. As a direct result of Margaret Kivelson's work, we now recognize that the ocean worlds may represent our best chances for discovering life elsewhere in the solar system. Her work has also led to the realization that many more planets and moons in the cosmos might host life than previously assumed. In doing so, she has revolutionized our vision of planets and moons as habitable worlds. So I'm very pleased to introduce the medal lecture of Margaret Kivelson, the best deserving recipient of the 2019 Jean-Dominique Cassini Medal and honorary membership of EGU for pioneering work in using magnetic fields to understand the interiors of planets and moons, which has revolutionized our vision of them as habitable worlds. Please, Margaret.
Okay. Well, thank you, EGU, for this great honor, and to my colleagues for giving up lunch or having it either too early or too late. I am going to talk about why we are interested in periodicities in planetary magnetospheres. And the reason I'm interested in periodicities is they tell us a great deal about the properties of the systems we're looking at. We can often probe remotely environments, different types of processes by looking at the waves that are associated with their presence. So, for example, Jupiter's rotation rate was accurately established by measuring the period of varying power of decametric radiation. The tilt of its dipole moment was established by monitoring the changing polarization of decimetric radiation. Exoplanet radio frequencies are being examined with great care, with the hope that they will reveal periodic modulation that may enable remote determination of magnetic properties. And back to Jupiter, currents between Io and Jupiter's ionosphere trigger emissions detected periodically at preferred orbital phases of Io. So if we hadn't known the orbit of Io, we could have figured it out, the orbital period. And these remote observations established the existence of Alphane wings. So periodic phenomena can monitor a system and tell us about its dynamics. For example, PI2s, which are quasi-periodic pulsations, are used to establish the times of substorm onsets at Earth. Waves can identify boundaries in plasma distributions, and Whistler waves, for example, were used to track the boundary of the plasmasphere, the plasma pause. And we can characterize the plasma and content of closed flux tubes by looking at resonant ULF standing waves. So there are lots of utility in these periodicities, and I'm just going to go through a few of them, naturally with an attempt to lead to the latest puzzle that I'm trying to work out. So these periodicities that I'm talking about may be externally imposed, or they may be internal resonances. The sources are not always unambiguous, but some of them are. There is a variation in geomagnetic activity that tracks the 11 or 22-year solar cycle. There are annual responses in the magnetospheric dynamics. I'm talking mainly the Earth on this, to orbital motion. There are diurnal responses related to planetary rotation, and there are internal resonances like ULF waves. And in seconds to minutes, there are a lot of things that relate directly to ion and electron motions. So you'll notice I'm going from low frequency to high frequency, and I'm really not going to talk about the lowest frequency. Let's go to the uncertain sources. Saturn is is penetrated, the whole magnetosphere, by near planetary period oscillations. They've been designated planetary period oscillations, but it's not the rotation period of Saturn, and they are probably driven by atmospheric flows. There's a secondary system at Jupiter, which is not the rotation period of its deep interior. It's repeatedly been observed in different phenomena. Some people think it's driven by energetic electrons that are slightly slower in rotation than the internal rotation period of Jupiter, but we still don't know if that's the real source, if that's just a secondary phenomenon. And there are repeated reports of near 1 hour periodicities, and I'm going to suggest that possibly some of these have a source in the solar wind. So I'll discuss only the longer period waves that that develop on large spatial scales. All right, so planetary magnetosphere studies started with observations of periodicities associated with Jupiter. Burke and Franklin, 1955, reported a source of variable 22.2 megacycle per second radiation has been detected. It lasts no longer than the time period for a celestial object to pass through the antenna pattern. The derived position in the sky corresponds to the position of Jupiter. And Higgins et al. Tell us that periodic electromagnetic signals at decameter wavelength emitted from Jupiter were the first discovered planetary radiation and the first evidence of a planetary magnetic field. So that's 1955. The radiation was initially thought to be, and it indeed is, emitted from high latitudes, where accelerated electrons carry upward field-aligned current out of the ionosphere. And the cutoff at 40 megahertz was interpreted as evidence of a maximum field near 14 Gauss, and we still find that that's roughly right for the maximum field. The period was identified as Jupiter's rotation period, which at that time was known only from tracking cloud tops, and you know they don't stand still, and so we didn't have a decent rotation coordinate system, but after we found this rotation period, we could define a coordinate system that remained fixed. The most extensively studied magnetosphere, of course, is Earth's. And what we know is that geomagnetic activity peaks periodically. Quite a few people have been unfortunate enough to send up spacecraft to study geomagnetic activity at solar minimum, and have had a lot of trouble finding the storms they want to study. So it's quite clear that there's a variation that relates to the solar cycle. Some periodic variations are semi-annual and diurnal, and they're attributed to what is referred to as the Russell-McFerrin effect, and it's linked to reconnection at the subsolar magnetopause. The effect arises from the tilt of the rotation and dipole axes and their relation to the average solar wind direction. And so I have a rotation axis shown tilted. This is at equinox, and I'm the sun, or you're the sun, and we're looking toward the Earth, and so this is dawn and the dawn-dusk direction, and the rotation axis is tilted toward, in this case I'm showing it tilted toward dawn, and the magnetic axis rotates around it, causing an effect that could be related to reconnection with the average solar wind direction. So we have a rotation axis that's fixed in inertial space. I just want to be sure, yes. It's fixed in inertial space. In northern winter, it's pointing away from the sun. At spring equinox, it's pointing toward dusk. At summer, et cetera. And meantime, the solar wind is, when in a favorable orientation, is reconnecting near the subsolar magnetopause. And in March, when the equinox, when the axes tilt in the plus in the direction toward dusk, as I've shown here, the reconnection is optimized when the solar wind magnetic field is on the spiral pointing toward the sun. In September, the reconnection maximizes when the solar wind magnetic field is pointing on a spiral direction away from the sun. And that has been confirmed by data. It was a very good support for the idea of reconnection as relating to geomagnetic activity, and it is a periodic variation that has a strong semi-annual variation, but the fact that the tilt increases and decreases at a given season, depending on time of day, can also be detected. There are other periodic diurnal changes that are controlled internally by the dipole tilt. So when the dipole north tilts toward the sun, the current sheet in the tail tilts upward, and in the 12 hours later, it tilts downward. The effect has been observed in the magnetotail with studies from IMP 7 and 8 and ICE data long time ago, This is a cut through the tail at roughly 25 RE down the tail, and it shows the polarity either toward the Earth or away from the Earth in the tail. And what you see is that when the dipole tilt angle is small, roughly here the cases are all less than 5 degrees tilt, you get this very symmetric tail, and you can see the position of the magnetopause is the break between a rather constant orientation and a random orientation. You see that both for small dipole tilts and for large dipole tilts. And you can also see that the tail current sheet has a very different shape when the dipole tilt angle is large. And so the field magnitude remains the same in these two sectors because of pressure. We need that for pressure balance. So the magnetic field and the magnetic flux remain identical in the two lobes, even in the distorted simulation configuration. Another example of external control of the periodic reconfiguration is found in Ganymede's mini-magnetosphere, which is embedded in the ambient field of Jupiter's magnetosphere, and that, from the perspective of Ganymede, rocks back and forth every 10 hours. And what you see is not only very marked differences in the magnetospheric configuration, but also rather substantial changes in the intensities of field-aligned currents, which are being shown in color here. And you can see that when the tilt is in direction labeled A, there's a very strong field-aligned current on the side of Ganymede facing Jupiter. Jupiter's off to the right, and that weakens as you change the tilt. So there are lots of features of the magnetosphere that vary at the 10-hour period of the external field. Io's plasma torus, many properties are internally modulated at Jupiter's rotation period, which I mentioned was system 3, but there's also this slightly, actually it's longer period. No matter how many times I go over my slides, there's always a typo. It manifests itself intermittently. It's not seen all the time, but here's an example from work of Steffel, in which he is looking at the composition of the torus plasma, different ions. This is singly charged sulfur, doubly charged sulfur, triply charged sulfur. And interestingly enough, they seem to vary in antiphase, but there's a periodicity. And that periodicity that jumps out at you is the rotation period of Jupiter. And here we have the electron temperature and the electron number density. They're also varying in antiphase at this rotation period. But what one can see is that if one plots the amplitude of the maximum to the minimum in any of these parameters and plots it over long periods of time, seems to be a variation in the amplitude with a period of the order of 20 days, and that has been interpreted as the beat period between the rotation period of Jupiter and this longer System 4 period. And that's one of the ways in which System 4 has been discovered, and it is found that a model that introduces a very small population, 0.2% of slightly subco-rotating superthermal electrons can mimic these variations. But I think we have lots to do to figure out what really starts the whole process. So the source and maintenance of these slower rotating electrons is not yet established. At Jupiter, the rotating tilted dipole is the principal source of periodicity throughout the magnetosphere. Its varying orientation causes the central current sheet to bend and the tail to flap at a 10-hour period. And what I've plotted here is for many days, the radial component of the field in black, and it's negative during part of each 10-hour cycle becomes positive, negative, positive, negative. That's just because the spacecraft, which is at a fixed position in the magnetosphere, is in a position where this tail current sheet is going up and down over it with a 10-hour period, going down and then back up, and the spacecraft is seeing the outward directed radial field when it's in the northern lobe and the inward directed radial field when it's in the southern lobe. And so again, we learn a lot about the global structure of the magnetosphere by studying these 10-hour periodicities, and they've been used to learn a lot about the magnetosphere. And the flapping is extended down tail to distances as large as we've been able to explore them. So we expected that Saturn's magnetosphere would also flap up and down, pretty much like Jupiter's. And we were wrong about pretty much like Jupiter's, although we were right that it goes up and down. So the periodicity of power in Saturn's kilometric radiation, which is a remote way of studying what's going on at Saturn, was identified first in data of the Voyager spacecraft in 1981. And of course, at that point, we had no reason to think it was different from Jupiter, that it was a tilted field with a period imposed by planetary rotation. So the periodicity of this Saturn kilometric radiation, of the modulation of power, was accepted as Saturn's rotation period by the International Astronomical Union. But then Ulysses went out toward Jupiter, and a surprise was that the SKR period had changed over time scale of years, which is far too fast to be interpreted as the change of a deep internal dynamo field. So that left us with a big puzzle, too rapid to be evidence of the properties of the deep interior, so it wasn't like Jupiter, and it wasn't being imposed by planetary rotation. And then Cassini went out to Saturn, and after some time in orbit, this is 8 years, I think, 6 years, analysis showed that not only was there the dominant period that was near 10.8 hours, the scale over here is in hours, and it goes from 10.5 to 11, but there was actually also a shorter period, and further studies showed that the dominant period was the longer period was coming from southern hemisphere sources in Jupiter's ionosphere, and the shorter period was coming from the northern ionosphere. And that made it clear that there was something going on in the ionosphere that was rotating with the planet, but not necessarily completely linked to its deep interior. And but the measurements of the magnetic field could not find any departure from axial symmetry. Neither its dipole moment nor any of the higher moments are other than aligned with the rotation axis. And so what is producing that periodic variation? Well, I'm going to get back to talking about the source, but I just want to show you through a movie of a simulation by Jha et al. That puts a source of anomaly in the, in this case, both one in the north and one in the south in the ionosphere, and looks to see how it affects the magnetosphere. And what you can see is that the entire magnetosphere breathes and deforms. The current sheet on the day side extends out, pushes out the magnetopause. In the tail, the current sheet flaps up and back, not up and down, but up and back. And what you can notice is that the color is density, and it's actually a pretty good proxy for pressure. And what you're seeing is waves propagating out, much more intense in the south than in the north, and that's during southern summer when the southern source was more intense than the northern source, and it's pushing the current sheet up and back. So I think I've said all of this. So this is in this simulation, there's no dipole tilt, and the effect is produced by compressional waves that are propagating outward from sources in the ionosphere. So it's very different from Jupiter, very different from Earth. So the flapping of the tail current sheet is only one of many properties of Saturn's magnetosphere that pulse at the SKR period. Pioneer and Voyager data already had revealed periodic signatures in magnetic perturbations in the equatorial plane. Cassini observations clarified their structure, and the polarization characteristics required a source external to the planet, so it became clear that there had to be a system of rotating field-aligned currents that was somehow playing the source role for these periodicities. And near the magnetic equator, this is a movie of actual observations of the perturbation magnetic field near the equator, and it's quasi-uniform, and it's rotating at the 10.7-hour period of these planetary period oscillations. But there are many more periodic responses. There are periodic energetic neutral atom enhancements. There's rocking of the auroral oval. There's flapping of the tail current sheet, thickening and thinning, as well as flapping of the tail current sheet, magnetopause displacement, plasma density variations, preferred phase of plasmoid release in the tail. All of these are governed by the planetary period oscillations. But we still don't know for sure what imposes the periodicity at Saturn. So that's a big outstanding question. But we do know some constraints. The two periods are, on average, relatively stable, with changes of no more than 1% or so a year, and they return close to a predictable phase following large-scale perturbations of the magnetosphere driven by the variable solar wind. So that's something that's quite clear. Sources must be at high latitudes in both hemispheres and independent of one another because they function at slightly different periods. Summer hemisphere period is typically the longer one. We think that it's pretty clear that this requires that the source of this quasi-rotational periodicity is in a region of significant inertia, but it has to be a region that interacts closely with the ionosphere, and therefore it has to be the very high atmosphere, the thermosphere, that's some feature of that rotating at the observed period. And as I've pointed out, the response in the magnetosphere requires field-aligned currents coupling the two regions. So vortical flows driven independently in the northern and southern thermosphere and rotating at the planetary period, the planetary oscillation period, could drive a system of field-aligned currents into the magnetosphere. And back to the simulation by Jha et al., that's what this simulation does. It puts vortical flows in the high latitude ionosphere, separately rotating in the north and south and rotating at the observed period. The strength of the vorticity is chosen to drive field-aligned currents that can make the observed perturbation magnetic field at the equator. And the position of these vortices is centered where we know that the field-aligned currents flow. But those are the input, and what you see is that the magnetosphere, again, this is an equatorial cut, that all sorts of things develop periodically from these very localized sources of currents in the ionosphere. The magnetopause is going in and out. It's I'll come back to that in a minute. There's a ring, the color is current, transverse current, and so there's a ring current that's modulated at the oscillation period. Great many things. The whole magnetosphere is responding periodically. So we'll look at how these sources, more about how these sources drive responses. The perturbations launched by the rotating vortices are not only directly driving field-aligned currents, they're also introducing pressure perturbations into the system. And here is another one of the movies from the simulation. And here, the open-closed field line boundary has been indicated, so you can watch the magnetopause go in and out. Here we're looking at pressure, and what you'll be able to see is that there's a pressure pulse that gets generated, goes out and pushes out the magnetopause, pushes it out asymmetrically, and it always goes farther out on the morning side than the evening side. So the entire boundary breathes, but it's asymmetrically following a rotating compressional perturbation. And compressional waves are launched down the tail. They're periodic, but they're phase delayed, and so you see the current sheet flapping, but with a delay down the tail. Highly disruptive of the magnetic geometry. The magnetic shells, even close in, are very greatly distorted. And here what's been done is to draw a contour in the equatorial plane showing the intersection of a flux tube starting at invariant latitudes 65, 60, they're 1 degree separated from 65 degrees latitude to 73 degrees latitude. And of course, the low latitude invariant latitudes intersect the equatorial plane close to the planet, and the high latitude intersect far from the planet. And what you're going to see is how the pressure pulses distort these shells of constant invariant latitude. And another way of seeing what's going on is in this diagram, where you can see that the thing that is causing the funny behavior in the midnight to dawn sector is the release of a plasmoid. Now, we have not, in Cassini data, found a plasmoid released once per cycle, as this model shows, but what we do know is that there's a preferred rotation phase at which the plasmoids are launched. So the simulation is not exactly modeling the behavior of the magnetosphere, but it is doing a lot toward it. Of course, we've, for decades, have studied resonant oscillations of flux tubes at Earth. They can be seen from ground or in data from magnetospheric spacecraft. They're diagnostic of magnetospheric and ionospheric conditions, and so we have different harmonics of resonant field oscillations that are standing on dipole flux tubes. In the WKB approximation, the nth harmonic its period can be very well approximated by just integrating the inverse Alfvén speed over the flux tube. And you can see that the Alfvén speed is very, very strongly dependent on the magnetic field. It varies linearly, so most of the contribution to this integral comes from near the equator, and so it gives you a good way of estimating the equatorial density by working out the relationship between the period and the density. And these resonant fields are stimulated in different ways, but one way is through a Kelvin-Helmholtz wave on the boundary of the magnetopause, and so this is the magnetopause boundary. Amplitude decreases as you propagate in, but if the frequency on the boundary matches a resonant frequency, you get an increase in amplitude, and this shows you that you get a reversal of polarization by 180 degrees across the resonant field line. And these resonances and their polarization match very nicely observations. So finally, I'm going to get to the quasi-periodic one-hour waves that are observed in fields and particles at Jupiter and Saturn. And here's an example in which we're looking at three components of the magnetic field and its magnitude. The amplitude of these oscillations is not very large, but I think it's quite clear, and the periods are not always 1 hour. In this chart, the vertical lines indicate 1 hour separation, and so you can see they're a little longer than an hour, but that's what we mean by quasi-periodic 1 hour waves. In some cases, the amplitude of these waves increases every planetary rotation period. And what you can see that very nicely in this plot that has been shifted by 10.7 hours, twice 10.7 hours, and 3 times. So you can see that the phase of the rotation at which these things appear seems to line up. But this is not a typical case. This is a special case. However, Rositas has looked through, I think, the whole Cassini data set and has identified these quasi-1 hour period fluctuations. Now, one of the problems with trying to figure out where you see them is this is a plot of the number of hours that Cassini spent in different latitude local time cells. And you can see that most of the data come from close to the equator. So you have to be very careful in figuring out what's the most probable place to see these events. But if you normalize number of hours of observation versus number of hours in the bin, what you can see is there's a preference for high latitudes. So there's also a big gap in local time. So we don't know the full story, but they do seem to be at high latitudes. And so what Rositas has done is to take the Saturn magnetic field model of Khurana et al., and he has looked where he sees one of these events and mapped it down into the ionosphere. And on the right, you will see the red dots are launched from day-side sources, the blue dots from night-side sources. What you can see is The shaded region is the average auroral zone, and these events are either in or even poleward of the auroral zone. They seem to be very much favored to see these periodicities on field lines that go either directly into the solar wind or very close to the solar wind and the magnetopause boundary. Now, there is an interesting observation that's been made in the solar wind near Earth. Kepko et al. Found that quasi-periodic compressional perturbations in the solar wind are frequently centered around 1 hour, and that they drive long-period compressional waves at Earth. So this is a set of observations from GOES in the magnetosphere in the very gray color, and black is wind data. And it's been detrended in the second plot, and I hope you can see. There's sort of a purpley color. There's a very high correlation between, the wind data have been shifted by 60 minutes. And both at GOES and on the ground, there's very high correlation between the pulsations seen at wind and the pulsations seen at GOES. Now, do we see 1 hour pulsations in the solar wind near Saturn's orbit at 10 AU? For me, it's very hard to imagine that any compressional pulsation will survive 10 AU, but we did find 10-hour periods in the solar wind data taken by Cassini near Saturn. So how they get reinforced or reinvented, I have no idea, but they clearly are there. And so the next question is, how long do they last long enough to make a compressional pulsation? Well, Vial et al. Reported trains of compressional pulsations with this roughly 1 hour period and a length scale that translates to 20 Saturn radii. And that scale is unlikely to change with outward propagation. And so if I put 20 RS waves across the magnetosphere of Saturn, it's confusing. They would affect a large part of Saturn's magnetosphere. It seems quite plausible that they could make a quasi-Kelvin-Helmholtz disturbance of the boundary and propagate these 1 hour waves into the magnetosphere. And they would affect primarily the high latitude flux tubes, which fits with what has been seen in this study. So this suggestion requires further testing, but seems a plausible interpretation to me. There must be something else going on because the periodic recurrence at the SKR period is a little puzzling, but you know, the magnetosphere compresses and expands independently on the SKR period, and the compressional pulsations may be more effective for an expanded magnetosphere or maybe for a compressed magnetosphere. So this is still an area that needs further investigation. So in summary, low-frequency periodic phenomena are ubiquitous in planetary magnetospheres, and I've looked at only a selection of periodic responses, and there are many questions that remain. So I'm left with questions like what physical process generates the rotating field-aligned coordinates, currents that are present at Saturn? Is it possible that Jupiter's System 4 period is generated in the same way as the planetary period oscillations of Saturn? It always seemed plausible to me. And I leave you with thoughts about long-period waves in planetary magnetospheres. For years, I would sit at AGU meetings and get really bored with looking at the wiggles on charts. But the waves are not just wiggles on charts. They're diagnostic of conditions in large parts of the magnetospheres in which they are present. They may be internally driven by magnetospheric instabilities, or externally driven by the solar wind, or as we saw at Ganymede, the planetary magnetic field. And Saturn's example suggests that they may even be driven from the ionosphere. So thank you, and I'd be happy to answer questions.
Thank you. Now it's working. Thank you, Margaret, for this inspiring lecture. I'm sure that the audience will have questions for you. I saw an hand raised and another here. Please, if you could go to the microphone so everyone can listen to you clearly.
Thank you. I think through all the complicated interplanetary plasma physics, the Alado phenomena, you dig out one of the most important aspects that is the question is periodicity. Also is with wave. Wave is periodic too. So I think you open the door for us to think about the future, because we need to do one thing, like you said, is you didn't directly say, is a topological approach, including magnetic hardicity, like vorticity, all those things. We already started to do. And also, we need to talk about the wave-particle duality, this to emphasize the wave-packet dynamics. And we have the nonlinear interaction, because two wave packets interact. They give us high-energy charged particle acceleration because they produce electrostatic E field. So I think you gave us the future, and I'm touched that you gave us the trigger to talk about how to do physics.
Well, thank you for your remark. I think we talk about that after the lecture.
There was another question, please.
Well, the periodicities at Saturn are seen very clearly, because the other kind, they just do the dipole tilt, is absent. I think it's an interesting question.
The tennis, my hearing is not good, and I just cannot understand the question.
Okay, sorry, I'll try again. No, the oscillations at Saturn are very clearly visible, because the other kind, the dipole tilt, is absent at Saturn. But I think it's an interesting question. Supposing Saturn did have a dipole tilt of usual sort, a few degrees, and but all the other phenomena, which are now assumed to be there, were still there, would not have seen all those planetary oscillations, or would have been completely swamped by the dipole tilt effects in there. And that leads then to the question, if they would not be completely swamped, are there such oscillations at Earth and Jupiter, as at Saturn, but are not being seen because of the dipole tilt of these planets is very strong? And the final question on this is, it looks like even interprets the oscillations of Saturn as being of thermospheric origin. Then we have a very large thermospheric effects in the magnetosphere, in the outer magnetosphere, which I think are not seen at Earth, as far as I know.
Please.
I'm just going to say thank you for your comment, but I regret I have such serious hearing problems. I can't give you an answer now. I'll talk to you afterward.
I think you can maybe discuss the comments later after the lecture, but I wonder if there are other questions from the audience that are real questions and that can be stated in just a few words. Because, yeah, you know, I understand it's a very nice debate, but these are comments that need a longer discussion. So I would encourage the audience to be very synthetic. Please.
Okay, I have a very clear question. It was, as NASA is maybe planning a mission to the ice giants, can you comment maybe about what do you think would be interesting to study in terms of periodicities in the magnetospheres of the ice giants planets?
I'm sorry, NASA is planning a mission where?
It's a project, it's not sure yet. But,
yeah.
To Uranus or Neptune.
Okay, question was about periodicities at the ice giants. And, you know, the magnetic fields of the ice giants are extremely complex. And so that's, to begin with, we're going to learn a lot about the internal field of the ice giants just by looking at the form of the time-varying measurements that we're making. But I'm sure we're going to find extremely interesting and extremely challenging low-frequency periodicities at the ice giants. If I answered the question you asked.
Yeah, please.
Keep it short, please. Because
Yes, actually, I wanted to paraphrase Vitenis's question. Do you think that the fact that we can see these subtle effects like the planetary period oscillations at Saturn is primarily due to the fact that the dipole tilt is absent? And could similar effects be present but masked by dipole tilt effects at Earth and Jupiter?
Could the periodic effects arise from dipole tilt, right?
Well, you wouldn't see them at other planets because the dipole tilt effects are stronger.
I see. You wouldn't see them because dipole tilt effects are strong. Yeah, I think that's why it's been so hard to detect this transient system 4 periodicity, because it is heavily masked by the system 3 period, everything changing at the system 3 period. So you have to, basically, you noticed what the example I showed you, what you're actually looking at is the beat period and inferring the fundamental period from the beat period, which I think is probably the most powerful tool for looking for system 4. Yeah, I mean, that's a real problem and a very sensible comment.
We have time for one more question, please.
Okay, thank you. Can I first of all just thank you for being an inspiration for us other women who have followed you. And I'm great that you got your talk today. And my question is, you talked about periodicities a lot, and you talked about different sources. Could you say something about maybe looking about bicoherence or correlation between these signals? Is there anything been done, or is there anything possible to do with this on planets? I mean, I know we can do it at Earth, obviously, to look at how that works. No? So if you have two signals looking at, you know, how they are phase coherent, that's what I'm asking.
Correlation between two signals, two periodicities.
If you have two sources, and they're phase coherent. No? Okay. I'll ask you after.
I apologize, but didn't get it.
Okay.
So, sorry the question period was a flub.
Yeah, but I invite the audience to maybe take this opportunity for talking directly with Margaret. And I really would like to thank you, Margaret, and to congratulate again on behalf also of the audience and the EGU Council for this very wonderful achievement. With that, I'm closing this medal lecture. I would like to thank the audience for attending and for asking provoking questions. And again, I suggest to take the opportunity to talk directly with the speaker, because I suggest that indeed we take this interesting opportunity to talk and to comment on the results of an entire life dedicated to these important research topics. Again, thank you very much also for attending this conference. Enjoy the last 2 days of it. Thank you.